Welcome to Developing Graphics Frameworks with Python and OpenGL, Part 32, Spheres and Ellipsoids. Along with boxes, spheres are probably one of the most familiar three-dimensional shapes. And so we'd like to learn how to render them in this video. In the previous video, you created a new class called Parametric Geometry, and that class is used to graph a surface, but you need to know the parametric equations of that surface. So, as long as we can figure out the equations of a sphere, we'll be able to graph a sphere. So, let's figure out those equations. It's actually not too bad. For simplicity, we're going to assume that the sphere is centered at the origin and has radius 1. And the way we're going to think about a sphere, we're going to think about taking cross sections of a sphere. So for example, if you have a sphere here, imagine slicing it through kind of along the y-axis, kind of slicing into pancakes from left to right. Now each one of those, we call them a cross section. Each cross section is going to look like a circle. So it turns out our starting point for the equations of a sphere is the equation of a circle once again. It's the same equations we saw when we were working with polygons. Except in this case, instead of setting the trigonometric functions to the x and y variables, we're going to think of those as the x and z variables. Again, we're slicing along the y-axis, so we're slicing kind of horizontally. And so each one of those slices, if we look down the x, or if we look down the y-axis, right, we're looking down at the x and z axes. Right, so these will be the equations for a circle of radius r. And this radius, the radius of the slice, is different than the radius of the circle. Right, you have different sized circles depending on where you slice the sphere. So if you slice it right along the middle, you'll get kind of the largest circular cross section. If you slice it closer to the top, your cross section will be a slightly smaller circle. If you slice it really close to the top, you get a circle with an even smaller radius. Right, so this value of r is not a constant value. It depends on where the slice is. In other words, r, you can think of that as being related to the y value. We'll figure out why in just a minute. So the cosine and the sine functions to go all the way around a circle. Of course, so we're thinking of these in terms of radians. The u value has to go from 0 to 2 pi. Now, to figure out what the y has to be, well, we know what the implicit equation of a sphere is. It's just like the equation of a circle, the implicit equation of a circle, but there's also a z coordinate. So the equation of a sphere is x squared plus y squared plus z squared equals 1. If we want to solve for y, then we could plug in these two equations. We can plug in r times sine u, plug that in for x, and r times cosine u, plug that in for z. Now if we plug those in and we use a trigonometric identity, sine squared plus cosine squared equals 1, it turns out part of this simplifies and the x squared and the z squared, that combines to give us an r squared. So after substitution, this equation becomes r squared plus y squared equals 1. It's a circle again. And so the easiest way to parameterize a circle is, again, by using cosine and sine. So again, let's use, for r, let's let that be cosine, but we need to use a different variable this time. Let's make that v. And y, let's let that equal sine of v. And in this case, we know that this is going to equal 1. This is the 1 from over here. And so there's no coefficients in front of this sine and cosine. Now we also need to know the range of v, and there's a couple of constraints. So whenever y is all the way at the top of the circle, sorry, the top of the sphere, right up here, when y equals 1, that radius is just a point. So it has no radius. The radius is 0. Down in the middle, when y equals 0, the radius at that point must be 1. And down at the bottom of the circle, when y equals -1, the radius again must be 0. And so keeping those in mind, right, what could the range of the v values be? Right? It needs to produce the y values from -1 to +1. And that corresponds to the values of -π/2 to π/2. You can also check when you have -π/2, y is -1 and that radius is 0. When v is π/2, then y equals +1, that's the top of the sphere, and again the radius is 0. And if you're right in the middle, if v was equal to 0, then y is also equal to 0, and the radius would be equal to 1. Right, so these equations just work perfectly to appropriately model those cross sections. So, well, what do we know? We know what x is. X is r times sine u, but we know what r is. R is cosine v. So putting those two things together, we know that x is equal to sine u times cosine v. Y is just sine v. And z, well, that's r times cosine u, but again, we know r is cosine v. So cosine u times cosine v, that occupies the z position. And that is the function for the surface of a sphere. With that little bit of math, or moderate amount of math, we're going to be able to create this equation pretty easily. Now, in addition to creating the equation of a sphere, there's a related shape called an ellipsoid, which we can make without too much extra effort, so we might as well. If we were to scale the x and the y and the z by some amount, we would get this general shape. But if the scale was equal in each direction, then we would just get a sphere. So the way we'll actually implement these in code, we'll say if we want to make an ellipsoid, we'll specify the width and the height and the depth of the ellipsoid. And if we want to make a sphere, then we'll just say all of those are equal to the same value. You get a nicely proportioned sphere. All right, that's the idea. The important thing, the important takeaway is the equation of a sphere. And we're going to use that to create a class, and create a couple of classes. All right, so let's go ahead and head over to Sublime Text. We're creating a new geometry class. So in the geometry folder, we'll add a new file. Again, I'm going to start with an ellipsoid and then derive a sphere from that. So let's save this first file as ellipsoid geometry.py. Okay. Again, these are actually relatively short because we did so much work in the parametric geometry class. Once again, we're extending parametric geometry, so we need to import that from geometry.parametric geometry. Let's import parametric geometry. And then, again, we need a little bit of math in our functions here. So from the math package, let's import sine, cosine, and pi. Oh, don't want to autocomplete there, just pi. Now let's make our class ellipsoid geometry. It extends parametric geometry. We'll define the initialization. And let's see what this would just look like right off the bat, and then we'll add the scaling parameters in a moment. Whenever we create an extension of the parametric geometry class, we need to specify the equation, the parametric equations of the surface. So in this case, if it was just a sphere, we said that that equation was sine u times cosine v. Put this on 3 lines so it's easier to read. Sine v and cosine u times cosine v. Right, those would be the equations for x, y, and z in our sphere. Right, and let's say, you always have to remember at some point to call the superclass initialization. And we need to say what the parameters are here. We'll spend some time thinking about those as well. For u, it's going to be 0 to 2 pi. We need some number of segments, I'll say, I don't know, 32. So we want this to look round. And then on the v, we need the lower bound. We said that would be pi over 2. The upper bound is pi over 2. Some number of segments, again we'll say 32. And we need to give it that function, s. All right. So again, this is our first pass. We're going to come back and edit this and generalize it a little bit more. But as it is, this should create a sphere of radius 1. So let's save this class. Let's make a test class so we can take a peek, see how it's doing. In the root folder, let's make a new file. This will be saved as test32.py. And once again, using our wonderfully useful template file, copy all the code from the template into our new test, and let's import our new geometry class from geometry.ellipsoid geometry, import capital E ellipsoid geometry. Half the battle is spelling it correctly. All right. Now, as before, we need to just change the name of the class that we're rendering. So down here, instead of a box geometry, let's make an ellipsoid geometry, which for now should look like a sphere. When we're done, we can save and build this class. Oh, see, super has no attribute. Oh, I think there must be a spelling mistake somewhere. There certainly is. I forgot the 2 underscores on the other side of init. Right, save that. Let's go back to our test. Let's build that again. Hey, that is a fantastic looking sphere. Very cool. Okay, now let's see if we can activate some scaling in this. So ellipsoid geometry, let's actually set some parameters here. Let's say we want to set width, the height, and the depth of the ellipsoid. Right, so think about these parameters as corresponding to the same things for a box. Right, this is the width along the x direction, the height is the y direction, the depth is the z direction. And then in this context, I want to think about these as kind of radii along each coordinate axis. So I'll take these components and I'll multiply them by width over 2. And then height over 2. And finally, depth over 2. All right. And this should allow us to create kind of squashy looking figures. Let's go ahead and save this, go back to our test, and test this out real quick. Let's say on our ellipsoid geometry, let's say I want to make the width 0.5 and the height 2, and I'll leave the depth at 1. Let's save that and build. See how that looks. Yep, sure enough. Just to get a better impression, let's also rotate it while we're here. In the update function, let's add self.mesh.rotate y by 0.01337, random number. Let's do a build. So now we should see a spinning ellipsoid. And so now you can really see that it's skinny in this direction and it's a little bit wider in the Z. Very nice. Okay, now let's go back to our original plan, and if we want to create a sphere, right, how are we going to do that? Well, we can extend the ellipsoid geometry class. Whatever the radius of the sphere is, we're going to set the width, height, and depth to be the same value. So let's make a new geometry class. Right-click, a new file. Let's save this one as spheregeometry.py. And in this one, we're going to import ellipsoid geometry because we're extending that. So from geometry.ellipsoid geometry, we will import ellipsoid geometry. And there's not much to do, which is great. Class sphere geometry. It extends ellipsoid geometry. Let's say define init self, and the radius will default that to 1. Now remember, width and height and depth, those are kind of like diameters. They're double the radius. So we should think about that when we call the super init function. And so we're going to say 2 times radius, 2 times radius, 2 times radius. Again, because width and height and depth are each like diameters, right? If the radius is 1, then the diameter should be 2. That's why we have that multiplication by 2 factor going on there. All right, that wraps it up for the sphere geometry class. One final test to make sure everything's in good working order. Save that class back to test32.py. From geometry.spheregeometry, let's import sphere geometry. And then, as usual, what do we need to change? Just right down here. Sphere geometry. Let's try it out with a large radius. Radius equals 2. Let's see how that looks. So building and, whoa! Radius 2 brings us up really close to the camera there. That was surprising. Let's make that radius 1. A little bit more manageable. There we go. All right, that's a great sphere. So again, a little bit of mathematics goes a long way. Anything we can think of the function for, we're going to be able to graph the corresponding surface. So in this video, we learned about spheres and ellipsoids. In the next video, we'll actually learn how to do 4 different shapes by being very efficient with our code. We'll do cylinders and cones, prisms, and pyramids. So we'll do that in the next video. Thanks for watching.